In this video, we are going to discuss the concept of effusion and Graham's law, which allows us to mathematically describe the process of effusion. So first off, I want to do a quick recap of what we just talked about in our previous lecture on the kinetic molecular theory of gases and one of the key results that we derived from this theory. All right, so specifically, I want you guys to recall this concept of the root mean squared velocity, or VRMS. And remember that this equation was presented. This equation that allows us to calculate the root mean squared speed for any molecule. All we need to know is the temperature and the mass of that molecule. And so in the previous slide, we used this equation to predict the root mean squared speed of oxygen gas at room temperature here, 484 meters per second to be precise here. And we saw how, in addition, we could use the basic relationships that we observe in our equation here to answer problems as the following. And we were able to rank the relative speed of gases, different gas molecules, based on their masses. Basically, we see that because of this inverse proportionality between the speed and the mass, we find that the lighter molecules will be moving faster. Okay, so if you crank up the temperature, crank up T, right, the molecules move quicker. If you have less massive molecules, because mass is in the denominator, then these molecules are going to be moving quicker. What I want to do now is use that relationship, this idea that temperature influences the rate at which molecules are moving and the mass of the molecules influences the rate at which these molecules are moving around, to describe two related processes. Ultimately, we want to get to the concept of effusion, but first I want to touch upon something that you guys are already familiar with, the concept of diffusion. So diffusion is basically the tendency of substances to spread out. And we can really leave it as simple as that, for this example. So let's say, for example, that I have 20 particles all kind of grouped, isolated on this left-hand side of this chamber. So we would all predict that if I remove the divider, if I remove this divider, then what's going to happen, of course, is that these atoms are going to tend to spread out throughout the entire space of that container. And remember, we talked about this early in the class that, gas molecules in the gas phase, more generally, is characterized by this tendency for the substance to expand to fill the entire volume of the container in which it's found. Okay, so we can see now that during the course of me saying that, we now have a roughly equal distribution of these particles on both sides of the container. Okay, now this rate at which that diffusion process occurred, of course, depended upon how fast these molecules are moving. So if we reset the divider, but now let's crank up the temperature. Let's crank up the temperature all the way up to 500 Kelvin. And so we can see that these little molecules are now moving faster. Well, of course, now when I remove that divider, the diffusion process is going to occur that much more quickly. Okay, so no real surprises there. Diffusion, the rate of diffusion is obviously directly proportional to how fast the molecules are moving, which is directly proportional, or proportional to the temperature at which that substance is found. And we know from our equation, it's also inversely proportional to the mass. So if we reset the divider here and we crank up our mass, let's go to a much heavier molecule here, and we'll take our temperature back down to the starting point. We can see that these molecules are now moving slower and slower, and so of course when we remove that divider, it's going to take longer for equal portions of the gas to be on either side of the container when we are at this higher mass. Okay, so with that in mind, we're now ready to introduce this related concept called effusion. So effusion refers to the leakage of a gas through a small hole. Okay, so here we've got it illustrated. There's a small hole in the side of this container, and gas molecules are escaping, flying out of that hole. And just as we saw with diffusion, the rate of effusion is again going to be directly proportional to the root mean squared speed of those molecules. Which means if we were to say add another type of molecule into this little box here, let's say put another, say blue molecules in here, right? And we say, call the red molecules A and the blue molecules B, right? We can use this relationship between the root mean squared speed and the rate of effusion to compare the relative rates of effusion for these two different gases A and B. So to see that, right, we're going to use this fact, as we just said, that the rate at which A escapes through the container, the small hole in the container, is directly proportional to the speed. If the red atoms are moving faster, they will escape at a higher rate. Okay, so direct proportionality. And of course, a direct proportionality holds just in the same logic for molecule B. So if we take the ratio of those rates, we end up with the ratio of those velocities. Now, remember that VRMS is equal to 3RT over the mass in kilograms square root. So we can express both of these VRMS quantities for A and B, and we basically just take A directly. We're going to take the inverse of B. Notice we've flipped the numerator and denominator there. And because both molecules A and B are confined to the same container here, temperature is constant, R is a constant, 3 cancels out, right? And we are left with this relationship right here. The ratio of the rates of these two different molecules, the ratio of rates of effusion of these two different molecules is equal to the square root of the ratio of the masses. But be careful here. Notice that up top here we have rate of A and rate of B on the bottom. Whereas on the right hand side, B is up top and mass of A is on the bottom. And again, this is a manifestation of this inverse proportionality between the speed and the mass that we see in our original expression for VRMS. Okay, so what we've actually done here is derived so-called Graham's law of effusion. Okay, so Graham's law of effusion is simply this expression from the previous slide. Okay, and so let's see how we can use this. Let's consider the effusion of a mixture of two gases. We'll again look at A and B. And now we're going to suppose that the mass of molecule A is twice the mass of molecule A. In other words, the mass of A is 2 times the mass of B. What we want to do is now predict rate of A, rate of B relationship. We don't know this. Okay, so we're going to use Graham's law of effusion to come up with an expression that describes the relative rates of effusion. Okay, so let's start off with the ratio just as we have it up here. So we're going to start off with rate A up top, rate B on the bottom. We're going to then put over here the mass B over mass A, and we have a square root of that ratio of the masses, right? And now we're going to use the fact that we know the mass of A is 2 times the mass of B. So we're going to get rid of these variables here. Oops, I'm going to put it as 2 times mass of B on the bottom, square root. Okay, where again, all I've done here is use that relationship given in the problem. Of course, mass of B is going to cancel out, which gives us this ratio of the rates as equal to 1 over square root of 2 Or, in other words, the rate of effusion of B is going to be equal to square root of 2 times the rate of effusion of A. And this makes sense, right? Because A is more massive, so A, right, is going to be moving slower. So then in order to equal the rate of effusion of B, you're going to need to be multiplying by some value larger than 1. And it turns out that because of this relationship, inverse relationship of rate to the square root of the mass, that value, that relationship, or constant of proportionality is square root of 2. Okay, so in one final problem for this mini lecture, what I want to do is do a little bit more computationally intensive example of effusion, where we're going to be looking at two identical containers. And one of those containers is filled with hydrogen, and the other container is filled with carbon dioxide. They're both at the same temperature and held at the same pressure. Let's suppose that we determine that after 1 day, right, so a unit of time is 1 day has passed, we find that 1.5 milliliters of CO2 have leaked. And we need to determine, because everything's under the same conditions, right, we want to determine how much hydrogen has leaked out in 1 day. Okay, so we're going to start off in this problem with Graham's law. We know that the ratio of the rates is equal to the inverse of the ratio of the masses with a square root power. Okay, but notice, we don't see anything about rates being directly mentioned in this problem. Okay, and so we have to think, okay, when we're talking about the rate of effusion, what we're talking about is the rate of escape, how fast these little molecules are escaping out of that little hole in the side of the container. So you can think about this as an amount of gas that's escaping per unit time. Okay, so rate of escape is the amount escaped per unit time. All right, so we could set up an expression here, right, using the units of the problem. Well, we know in the problem we're told that the amount, we're measuring this in milliliters. The unit of time in this problem is 1 day. And the unit of time is the same. So if we set up a ratio here, the unit of time will cancel out, and we will just be left with volume, the amount lost. So the rate of escape is directly proportional to, well, how much loss we have. How many of those little H2 molecules lost? What volume of H2 molecules left? Rate of escape of CO2, what volume of those CO2 molecules escape the container? Okay, so we now have an expression where we basically transformed Graham's law into this ratio of the masses taken to the square root as being equal to the ratio of the lost volumes for each one of those different gas types. Now, volume, we have one of those values. We know that 1.5 milliliters of CO2 was lost. We know the molar mass of CO2 and H2. So we can plug both of those in. We can plug in that volume. And then finally, we can solve for that volume of lost H2 during the course of this 1 day. Basically move our 1.5 milliliters up to the left-hand side here, and we should come up with a value of 7.01 milliliters. Okay, so what we've seen here is really an application of this concept of VRMS and seeing how VRMS is directly, proportional to that temperature, inversely proportional to the mass, and of course these things are shown up as a square root. And we've seen how this relationship that was born out of this kinetic molecular theory talked about in the previous lecture gave us some important practical ramifications. We saw that if we have a higher RMS, then that corresponds to a faster or higher rate of diffusion. We introduced the concept of effusion, or the leakage of gas through a little pinhole, and we saw the same increase in rate of effusion with increasing in that VRMS. Okay, and then finally we introduce this concept of Graham's law, which tells us that the ratio of the rates of effusion for two different gases is equal to the inverse ratio of the masses taken to the square root power.